Ask an RF engineer what impedance is, and you'll usually hear an equation: Z equals R plus JX. But here's the problem. You can memorize that formula and still have no idea what impedance actually means. So today, let's strip the math away and answer a much better question. What is impedance really?
Most people are introduced to impedance as resistance for AC, and that sounds reasonable. Until it isn't, because resistance doesn't depend on frequency. Resistance doesn't store energy, and resistance doesn't cause reflections. Impedance does all three. So impedance can't just be resistance with a different name. Resistance is simple. It tells you how much energy is turned into heat. Once energy enters a resistor, it's gone. Impedance, on the other hand, describes how a system responds to changing energy. Not how much is lost, but how energy is delayed, stored, and returned. That difference changes everything. At DC, nothing changes with time, so the system has nothing to react to. But at RF, voltage and current are constantly changing. Electric fields expand and collapse. Magnetic field, that difference changes everything. At DC, nothing changes with time, so the system has nothing to react to. But at RF, voltage and current are constantly changing. Electric fields expand and collapse. Magnetic fields build and release, and every component responds on its own timescale. Impedance is the measure of that response. Here's the simplest way to think about impedance. Impedance tells you how hard it is to make energy move right now. Not eventually, not on average, but at this exact moment in time. That's why impedance depends on frequency, because frequency controls how fast the system is being pushed. The most misunderstood part of impedance is reactance. Reactance is not resistance. It doesn't destroy energy. It temporarily stores it. Inductors store energy in magnetic fields. Capacitors store energy in electric fields, and then they give that energy back. But timing matters, and that timing is what creates phase shift, delay, and reflections. When a wave reaches a load, the load's impedance tells the wave how voltage and current must relate. If the wave arrives with a different relationship, the system can't satisfy both at once. The result is simple. Part of the energy keeps going, and part of it comes back. Impedance isn't just a number. It's a contract. A contract between energy, space, and time. When the contract is honored, energy flows cleanly. When it isn't, energy reflects. Once you understand impedance this way, something interesting happens. A question you may have heard before suddenly becomes impossible to ignore. Why 50 ohms? Why is almost every RF system built around that number? And more importantly, why does it work so well? 50 ohms is often treated like a rule, a standard, something you simply accept. But 50 ohms is not magic, and it's definitely not arbitrary. It sits at a very specific balance point between two competing goals: power handling and signal integrity. If your system impedance is very low, you can deliver a lot of current, but losses increase. Heating becomes a problem, and cables become thick, heavy, and impractical. If your system impedance is very high, losses drop. Signals stay clean, but power transfer becomes inefficient, and noise becomes harder to manage. Neither extreme is ideal. 50 ohms lives right in the middle. It's high enough to keep losses manageable and low enough to deliver meaningful power. It's a compromise, but a very smart one. And once that compromise was proven to work, it became self-reinforcing. Cables, connectors, instruments, everything evolved around it.
This also explains something else: why video systems often use 75 ohms instead. Those systems care less about power and more about signal fidelity, lower loss, cleaner waveforms. Different priorities, different impedance.
Impedance is not just a property of components. It's a design choice, a statement about what you value more: power, efficiency, noise, or bandwidth. Once you see that, the number 50 stops being a rule and starts being a decision.
This is why RF engineering looks so different from low-frequency design. You're not just connecting components, you're shaping how energy moves through space and time. When impedance is understood, reflections make sense, matching makes sense, and tools like the Smith chart stop feeling mysterious. If this helped you build real intuition, like and subscribe to RF 101 Explained, radio frequency made simple.